7.4 Ionization energy. The ionization energy is the amount of energy required to remove an electron from the ground state of a gaseous atom or ion. The first ionization energy is that energy required to remove the first electron. The second ionization energy is that energy required to remove the second electron, etc. It requires more energy to remove each successive electron. This chart shows us across the top the first, second, third, fourth, fifth, sixth, and seventh ionization energies and the elements that correspond to those energies. You'll notice that after the valence electrons are removed, there is a very large jump in the ionization energy. For example, sodium has one valence electron, and to remove that valence electron would require 495 kilojoules per mole. If we try to remove a second electron from sodium, we would have to dip into the inner shell, and the jump goes all the way up to 4,562 kilojoules per mole. This electron would not easily be removed. The blue staircase represents the point where the valence electrons have been removed, and then the inner shell electrons would be removed. And again, you'll notice a huge jump in energy between the two.
Ionization energy is the energy required to remove an electron from an atom or ion. It measures how strongly an atom holds its electrons. The first ionization energy, I1, is the energy required to remove an electron from a neutral atom. Considerably more energy is required to remove a second electron from the positive ion. This energy is called the second ionization energy, I2. As each electron is removed by ionization, the remaining electrons experience less electron-electron repulsion and a greater effective nuclear charge. Thus, each successive ionization requires more energy. This graph shows the way in which the ionization energies of the aluminum atom increase as successive electrons are removed. Notice that the ionization energy increases with each successive removal of an electron. However, there is an especially large jump in the energy required for removal of the fourth electron. From a knowledge of the electron configuration of neutral aluminum, can you account for this dramatic jump?
Sample exercise 7.5, Trends in ionization energy. 3 elements are indicated in the periodic table in the margin of your textbook. This is on page 260. They are sodium, sulfur, and calcium. Based on their position or their location in the chart, predict the one with the largest second ionization energy. The locations of the elements in the periodic table allow us to predict the electron configurations. The greatest ionization energies involve removal of core electrons. Thus, we should look first for an element with only one electron in the outermost occupied shell. The element in group 1A, sodium, indicated by the red box, has only one valence electron. The second ionization energy of this element is associated, therefore, with the removal of a core electron. The other elements indicated, sulfur and calcium, have 2 or more valence electrons. Thus, sodium should have the largest second ionization energy. If we consult the chemistry handbook, we find the following values for the second ionization energies for the respective elements. And again, you can see the large jump in the ionization energy for sodium. Practice exercise, which will have the greatest third ionization energy? Again, think about how many valence electrons they have. As one goes down a column, less energy is required to remove the first electron. For atoms in the same group or column, the effective nuclear charge is essentially the same, but the valence electrons are farther from the nucleus, as N is increasing from 1 to 2 to 3, etc. Generally, as one goes across a row, it gets harder to remove an electron. As you go from left to right, the effective nuclear charge is increasing, but the number of shells is remaining the same, or N is the same as you go across the period. There are two apparent discontinuities in this trend. The first occurs between groups 2A and 3A. In this case, the electron is removed from a p orbital rather than from an s orbital. The electron removed is farther from the nucleus, and there is also a small amount of repulsion by the s electrons. The second occurs between groups 5A and 6A. The electron removed comes from doubly occupied orbital. Repulsion from the other electron in the orbital aids in its removal. Sample exercise 7.6, periodic trends in ionization energy. Referring to a periodic table, arrange the following atoms in order of increasing first ionization energy: neon, sodium, phosphorus, arsenic, and potassium. We are given the chemical symbols for 5 elements. To rank them according to their increasing first ionization energy, we need to locate each element in the periodic table. We can then use their relative positions and the trends in first ionization energies to predict their order. Ionization energy increases as we move left to right across the row. It decreases as we move from the top of the group to the bottom. Because sodium, potassium, and argon are in the same row of the periodic table, we expect the first ionization energy to vary in the order sodium is less than phosphorus is less than argon. Because neon is above argon in group 8A, we would expect neon to have the greater first ionization energy. Similarly, potassium is the alkali metal directly below sodium in group 1A, and so we would expect the first ionization energy for potassium to be less than that of sodium. From these observations, we can conclude that the ionization energies will follow the order potassium, sodium, phosphorus, argon, and then neon. Practice exercise. Which has the lowest first ionization energy? Boron, aluminum, carbon, or silicon? Which has the highest first ionization energy? Sample exercise 7.7. Electron configurations of ions. Write the electron configuration for a calcium cation, a cobalt cation, and a sulfur anion. We are asked to write the electron configurations for 3 ions. To do so, we first write the electron configuration of the parent atom. We then remove electrons to form cations or add electrons to form anions. Electrons are first removed from the orbitals having the highest value of n. They are added to the empty or partially filled orbitals having the lowest value of n. Calcium, atomic number 20, has the electron configuration argon 4s2. To form a +2 ion, the outer 2 electrons must be removed, giving an ion that is isoelectronic with argon. Cobalt, atomic number 27, has the electron configuration argon 3d7 4s2. To form a +3 ion, 3 electrons must be removed. As discussed in the text preceding this sample exercise, the 4s electrons are removed before the 3d electrons. Consequently, the electron configuration for cobalt +3 is argon 3d6. Sulfur, atomic number 16, has the electron configuration neon 3s2 3p4. To form a -2 ion, 2 electrons must be added. There is room for the 2 additional electrons in the 3p orbitals. Thus, the sulfur ion electron configuration is neon 3s2 3p6. Remember that many of the common ions of the s and p block elements, such as the calcium cation and the sulfur anion, have the same number of electrons as the closest noble gas, making them stable. Practice exercise. Write the configuration for these ions.